See how smoothing can help us detect edges on signal, for example, from images. So imagine to yourself that you have a very noisy image with a lot of noise in the image. Now the signal is, as you see in the orange, very noisy. There are a lot of variations. But remember that an real edge in the image is something that really cause a difference in very, let's say, around some area, which is not very little things that cause rapid changes in the intensity, but an edge, something that is very pronounced. So all the very little noise right over here are not edges, are not real edges. They are probably noise, but this change right over here that you see, this is an edge that I want to detect. Again, we continue and we see a lot of noise that do some changes in intensity, in the amplitude, but this is not real edge. But when we go through here, this is a real edge. You can even see the clean signal in dashed lines. It's zero right over here and then change because there is an edge over here and doesn't change over here. But here very much change because there is an edge and the noise just go on him. Now, when we are doing smoothing with Gaussian, you see it's almost as the clean signal, but not exactly. Now, how we can capture those changes, those big changes in signal that really represent an edge, what we can do is take the derivative, for example, and in the derivative, in very big changes, very rapid changes and big changes, there will be a high amplitude to the derivative. So this is what we are doing. You can see the derivative in red. This is the derivative for the noisy signal. You see that it captures a lot of noise. Think of it that every peak in the derivative tells me that this may be an edge. So in the noisy environment, there are many edges, very little edges in everywhere. So it doesn't really tell me anything because all the image is just edges. But after the smoothing, you can see the green line. This is the derivative of the smooth signal. You can see that I can capture the real edges in the image, and the other part of the noise is just almost canceled totally. So I can just take the real maxima of the derivative here also as well. You can see that it's just correlated to the real edges. I can take the maxima and the minima, and those are the real edges. And if I look on the noisy derivative, I do have some peaks, but I have so many peaks that I'm not sure which peak to take. Here I know that there are really distinct peaks that I can take as the edges to see. You can see that it's very much correlated in the place to the real edge, and all the other noise is almost totally cancel out. So this is why smoothing can help you detect edges in a noisy image. This is it.